Any place where you're stuck? Preventing you from trimming that task? Go ahead.
So I don't know if this is for the task 2 for the trebuchet one.
Sure.
I do want to figure out at least like the basics of accounting for that excess energy, because it was very significant when I calculated the excess.
Right.
I'm thinking we can just put most of it into the movement of the counterweight downwards. And there's still going to be other stuff, but I want to say that's going to be the majority.
But the movement of the counterweight downwards, that's the whole point, right? That's the source of the potential energy, correct?
Yeah.
Okay. So I would say that the swinging of the arm is probably a significant chunk, right? So if you want to do the rotational mechanics to calculate the energy of that arm literally swinging through, however many degrees it's swinging through, that might not be a terrible thing. But I'm going to hold off on that discussion until next week when we actually do rotational mechanics, right?
Sounds good.
All right. Anything else? Go ahead.
How do we do question 2 on task 17?
17, got it. Oh, that one. Okay. It requires a little bit of poking. I want to say if it's in chapter 6 or if it's in chapter 13, but I think it's in 6. The idea is that there's going to be a certain amount of work required to lift a payload into space, right? We're discovering this with various things that we're trying to put into space. Namely, some of the parts for instance, Artemis that might basically be helpful to have in Leo. By the way, those of you who don't know, Leo is low Earth orbit. How high up is that? I give a number here, but yeah, 600. Anywhere between about 100 kilometers and 1,000 kilometers is considered Leo or low Earth orbit. There isn't a set number because there's something special about that number. It's just, if you want to think of it this way, it's the top of the atmosphere. So in other words, where air resistance becomes literally negligible. Okay. You know, the air doesn't cut off, right? I was talking to a group of 3rd graders, and they thought this thing called the von Karman line, which is 100 kilometers up, 62 miles up, literally they're stopping air. But you could totally breathe stuff all the way up, right? Because we make such a point of saying, what is the edge of space? And you know why we have to define the edge of space? This is the stupidest reason in the world. It's because people need to get that damn pin, right? That makes you an astronaut. So that's why people go up in that Blue Origin spacecraft, and basically when they get up to 62 miles, and then they come down, they're awarded the pin. I mean, it's really a dumb reason, right? There is actually a new field, what's called space law, and it's not just making it sound cool because you put the word space in front of it, right? The point is that a friend of mine teaches at Georgetown University, and he's in the field of literally how do we govern ourselves in space. And so the first question literally became, well, where is space, right? Because we got the FAA and other national air organizations that govern what planes do, right? Things like that. That's not space, right, bless you. But where does space literally start? Because our spy planes that go up even higher into the stratosphere, are they governed by space law? Well, no nation would agree to that, right? So it has to be beyond that. But how much up? I mean, satellites, I think we can all agree, are probably in space. So what's the dividing line between the two? They settled on this thing called the von Karman line, which is that 62 miles up thing. Right? But it's not because the air suddenly cuts off there, right? It's literally this graduation of air. It gets thinner and thinner until you get to basically, you know, negligible air resistance. All right. So the point about this question then is, how much work does it take to lift one of these things up? And we're going to make it simple. What's cool about work is, does it matter whether or not, what path you take? In other words, does it have to be on a rocket going straight up, or can it take kind of a, you know, curvy, let's take in the scenery way? Does it matter? No. Work is what's called the state function. All that matters is the initial state and the final state, right? That's all. So all we got to do is figure it out for one path, and we're good. So the point here is, now this is where the work energy theorem comes in handy. So I've got, what's my initial state literally?
0.
Meaning
Or-
what?
Hey,
Yeah, yeah.
we're at rest.
Yeah, we're at rest on the ground, right? Okay. So the ground is here. It's the initial state. And I've got some mass, call it m, doesn't really matter what it is, right? Okay. All right, what's the final state? Yeah, we got the mass at what altitude?
600 kilometers.
Yeah, 600 kilometers, right? So altitude, 600 kilometers. It's the final state. So I can draw this arrow that shows the motion I'm interested in. So the work is going to equal the energy of the final state minus the energy of the initial state, right? That's the work energy theorem, literally, right? Okay. What energy are we talking about here? We're talking about what form of energy? Is there any motion implied by this? Is the mass moving?
Potential energy.
Yeah, there's no implication of mass motion, right? It's, I've got a mass here, and then I have a mass there, right? It's a snapshot. There's no velocity vectors on either snapshot. So the point is, basically, it's not moving. So is kinetic energy a factor in this? No. So the only energy is
Potential energy.
potential energy. And of course, gravitational potential energy, because the chemical potential energy presumably stays the same in all those other kinds of potential energies. So we're just worrying about gravitational potential energy change. So delta U, let's call it. Well, to be clear, U gravitational. Right, so potential energy and gravitational. Okay, so how do you calculate U? Well, if we were anywhere close to the surface, what's the formula you know and love that you're using for your trebuchet?
MGH.
MGH. Is that appropriate here, in this situation? The answer is going to be no, but why? What are the letters that, do any of the letters depend on how high up you are?
G.
Yeah, G. I mean, that thing you measured, like task 6, right, or whatever, it was basically 9.807, whatever, meters per second squared. That's only true where, literally?
On the ground.
On the ground, right? It literally, it actually means sea level on Earth, right, on a perfectly spherical Earth. So that means that at 600 kilometers, are we violating that restriction?
Yeah.
Yeah, G is a lot less up there, okay? So we cannot use MGH because G is not a constant once you leave the Earth's surface. Even though we've used it as a constant all along for the stuff we've been talking about even in the tasks, this is one place where it doesn't work, which is why I wanted to ask this question. So what do you have to fall back to? This is the chapter 13 part you may have to look at.
It's the Newton's,
So U gravitational has another formula. It looks like Newton's law of universal gravitation, because it has an M1 and an M2
Last quarter. Yeah, I remember.
and a big G. Okay.
Oh, this.
So no, big G, not little g. Okay. And it's divided by R, and I believe the whole thing is negative. All right. The point being this: big G is what's called the constant of universal gravitation. And this one is a constant. This one is listed in your book. Not under the constants that we use like little g, that are constant for the Earth's surface. But this one is one of the fundamental physical constants. I'll just read it out here. It's 6.67 to 36 figs times 10 to the minus 11, so it's awfully small. The units are messed up like every constant. It's Newton meter squared per kilogram squared. You may see different units because Newton's is of course kilograms meters per second squared, right? So you can fold that in there and it turns into something really horrible. But that's okay. Why are the constants units always messed up? Why are they always so complicated and gross?
they're meant to convert between two
Yeah,
of these.
it really gives you the units of the answer in the right units, right? So in this case, we want it in joules, so that better have those kind of units. Okay. So let's check it out. Let's see if we get joules. Does everybody agree that U grav should be in joules? Okay. So, masses, 2 of them, kilograms squared, right? Which cancels that guy out, right? Okay. R is in meters. It's the distance from between the two bodies. Okay, we'll talk about that in a sec. The point is it's the distance. So we'll cancel one of the meters out, right? So newtons times meters is literally what? Joules, right? Because remember the basic definition of work is F times D, right? Force times distance. Well, newtons is force, distance is meters, meters is a joule. Okay. So that equation, at least that's the right units. Everybody find it in the text? Or on your online reference that you're using or whatever?
Yes.
Do find it because it is kind of important for this problem as you can guess. Okay. So if that is U grav, so this, is this a calculus problem? Because of course the book makes it into a calculus problem. Just let's apply this, right? So the work done is going to equal the final state, which is minus G. Okay, now we got to deal with the M's, okay? So we've got, what two masses gravitating? Obviously the spacecraft, M1, let's call it spacecraft, I guess, SP. And what's the other end?
Earth.
The Earth, literally. Right. All right, and it's going to be divided by R. Okay, now that's the question. What literally is R on the ground? So I've got my spacecraft on the ground here, and I've got my Earth like this, okay? Technically R is 0 then, right? Right? So Newton actually even points this out himself in Principia when he talks about the law of universal gravitation. I'll get to that in a couple of weeks. He says it's not the distance between the masses, it's the distance between the blank of the masses.
Center.
The centers. So, center of the spacecraft, center of the Earth, that's R. And that is a profound statement because it means that we can model every extended mass, in other words, a mass that has volume, as what?
Sphere. Point.
Yeah, a point, right? Not even a spherical point, just literally a point, right? 0 dimensional, right? Okay? And the idea is that all of the mass is concentrated right there. So think of everything as a black hole, pretty much, right? Okay. But the point is that it works. That is basically a great way of looking at it. So instead of 0, we're going to write 600 times 10 to the third. No, it's not 600 because it's on the ground. Wrong. Wait, so what are we going to write here? Literally the radius of what? Earth. So R, Earth, which I give up there, right? Okay. All right. So then I'm going to subtract off of this because it's a subtraction, right? This is subtraction there. Minus GMSP, M Earth. None of that changes. Divided by what now?
R Earth plus R lower third.
Right. So R Earth plus 600 kilometers, right? Of course, once you convert the 600 kilometers, or for that matter, the, what is it, the 6,371 kilometers to what units? Convert them to meters, otherwise you get way too big a number. Reasonable? Seem reasonable?
Yeah.
Okay, great, okay. So the idea is that the work done literally only matters about the final and initial state. I just realized these close the parentheses here. There we go, okay. And the idea is that you can use calculus to calculate something like the work by doing the integral of this U grav over, well, not U, but force over that distance, but you don't have to generally because of that state function thing. All right, is everybody okay with that? Okay, great. Okay, so what's funny is in part B, Robert Heinlein, the famous science fiction author, came up with this notion that if you can get your ship into this low Earth orbit, you're halfway to anywhere in space. Okay? And I want you to assess that. All right? And you said, how do I assess that? Well, where is anywhere? Okay, if he literally means anywhere, what's the furthest distance you could go?
The other side of
Like Mars.
I'm not thinking of a place so much as a number for a distance. What's the biggest number you can think of?
infinity.
Infinity, sure. I mean, what's his face told us that, right? The Captain Buzz Lightyear told us that, right? I mean, he's going beyond too, but at least infinity, right? Okay. So my point is, if you want to go anywhere, which number? You do the same calculation, except you replace which number literally on this equation. Right. So we still keep the ground, right? So it's still going to be our Earth, right? Okay, but we replace this guy, this whole red thing in the denominator here, by what? Infinity. Which means this whole parentheses thing becomes what?
Zero.
Zero. So it's just literally this number, right? So you're comparing it against that number. And if this number is twice the number you got for this thing, then his statement is true, right? Then his statement is true. I'll give you a spoiler alert. He's a science fiction writer. How much math do they do?
None.
Yeah, the dirty little secret is you don't need to know math or science to be a science fiction writer, right? You just gotta have a good heart. Actually, that's a little bit more true than you think, right? A lot of science fiction authors that I've talked to are using science fiction as a mean to convey human condition stuff, right? So the technical details of it don't matter so much. Yeah. I run into the occasional what they call hard science fiction writers who basically talk to people at JPL and at Johns Hopkins and places like that and say, okay, this my spacecraft makes sense. Most famous example is the dude who wrote The Martian, Eddie Reardon, right? Very good. Yeah, I mean, he did so much research for that. But that's the exception, rather. Most of the time, basically, people just make up stuff like this. It's good to check their statements every so often because, when a random person hears this, oh, Heinlein's a famous science fiction writer, he must know about science, right? That's the assumption that's often made. We gotta check these guys and make sure they're staying within their sandbox, right? Yeah, I dig how you're talking about militarism, but you know what? Yeah, that statement not so much true. Yeah, you'll discover that it's not so much true. If that were true, how many space stations would we have that are actually launching things? Well, a hell of a lot more than we have now, right? Because if that's really true, it means that we just basically just build our spacecraft on that platform and just launch from there. Now, it still may turn out to be a viable, strategy for getting into space, but the fact that we haven't really, seriously studied it seems to indicate there's probably some flaws in that kind of thinking. In fact, where are we thinking we're going to do deep space exploration from? Where's the launch point going to be if we don't use the Earth's surface?
The moon.
The moon, right. And it turns out the moon's energy, gravity well doesn't add that much more energy than being in low Earth orbit. In fact, it's less. So the point is the moon technically is an easier place to launch from. All right. So anything else?
Oh,
Go ahead.
so was it task 11?